Hey, hello, and welcome. Welcome to this new and historical semester of online learning, and it's Physics 121. And this is our first lab, and I thought I would begin by taking about 10 minutes here out of the beginning and saying, all right, what and how are we going to do these online labs? So, presumably you got my email last night that kind of explained the whole class, and in that email I said that each Monday, and so here we are, Monday morning, I would go ahead and do a online lab and send it out to you Monday afternoon, maybe late afternoon, or maybe in the evening, depending on how long it takes. And so that's what I'm doing now here. And so this is going to be our first online lab. And so, like I said, we will do one lab each week. You got the syllabus, and if you've got a chance to look at the syllabus, I hope you did. That was kind of my first instruction. Step one is, go to Canvas and read the syllabus. And if you read that, you'll see that we are doing the static electricity lab this week. And so that's what I'm about to make for you. And so I'm going to describe these labs as me and you working as lab partners. You see, in a normal setting, in a face-to-face setting, here's what we would do. Is you would sit at one of these desks here in the lab room, and you would have a partner. And you and your partner would go through and read the lab manual and follow those instructions. And then you would answer the questions, you would analyze the data, and you would turn all that in. And so what I'm going to do here today is, after we get done recording this, I'm going to send out to you this lab manual. Okay, and so you'll get this in a PDF form. Okay, and this lab manual, then you will write and answer the questions. Now, they don't have to necessarily be in the lab manual, so you probably don't need to print it. You could also type it in, but when you turn it in on Canvas, as you'll see, it says a PDF. And so probably the easiest way to do that is to use Word or Google Docs and type in the answers. If you do some hand ones, then scan it and send it in a PDF. Okay, and as I said in my email last night, I've activated Canvas, but I haven't activated it to the point that you can turn anything in. And so this first lab, I'm going to give you all week to do it. If this was a normal face-to-face setting, 3/5 of you would do this lab on Wednesday, another 1/5 of you would do it on Thursday, and another 1/5 of you would do it on Friday. Okay, and so in this setting, it doesn't matter when you do it. It's just due Sunday night. And so sometime between when you get this Monday night and Sunday night, you go through the lab. And like I was saying here, in a normal setting, you would work with your partner. And that is, I would start off and I would explain the lab, and I would spend here about 20 minutes showing you the equipment and how to use it, and then I would let you guys start doing it, and I would just kind of walk around the room. Obviously, with the pandemic, we can't do that. And so the best we've come up with doing these online labs is to do the lab in a way that your partner is me. I am your partner. And so kind of pretend that you're in the lab, that you're sitting at this table, and that we're doing the lab. And so you're looking on, and I'm going to do, obviously, the hands-on stuff. I'm going to be the one who grabs the equipment and does it. Sadly, that's the part about an online lab, is you're not going to be able to actually touch this stuff with your hands. But I'm hoping by watching the video, and maybe even to some advantage of being online, I could expand on the questions and what we're doing a little more detail than maybe you would get on your own. So there is some plus sides to this online lab. And the online lab, and particularly today's lab, is a little more what I'd call a lecture demonstration lab. In fact, today's lab really isn't any different than the first lecture. And so I'm assuming you've already seen the first lecture by the time you get to this, or maybe not. But maybe I should say you should, because I've gone through most of these in that lecture and have kind of explained what's going on. And the purpose of the lab then is to give you a kind of a second chance at learning the physics by you doing it yourself. Now, as you know, you actually being in the lab and doing it yourself is not possible in this pandemic setting. So that's kind of the bummer part of it. But I think that, like I said, the good part is you get to see it a second time and maybe even get a chance to have me expand on it. And there are some things done in the lab today that I didn't do in the lecture. So not everything is a repeat, but even if it is a repeat, I think that's good because it gives you a chance to see the second time. And as I wrote in my email about class, just like reading the book many times, it's good to see the science a couple of times because you just really can't comprehend advanced science ideas the first time. It's not like I can tell you once and you get it. You really need to see it a couple of times. And that's why I said, and I'll repeat here, you should read the textbook, then see the lectures, and then reread the textbook. And by the time you've done that, you've been exposed to it 3 times. And the 4th time then is when you come in here into the lab. And when we come into the lab, we do 1 or 2 of these principles that we're talking about in class. And that gives you a 4th time to see it. And then ultimately, there's a 5th time where you sit down and do the homework problems. And that's how our science class is designed. You get exposure to the same thing 5 times. It almost sounds like we're repeating ourselves. But the reality is you just can't learn it in your first reading. And you can't learn it in the first lecture. You've got to do it a couple of times. And in this case, 5 times before it truly sinks in. And so that's really the strategy of our advanced science classes. Now, the beginning science classes are a little different. You can learn that first or second reading, but not this material. So we're giving you 5 opportunities here to really digest this. So with that all said, again, think of me as your lab partner, okay? And this is the equipment here for today. And so I'm going to work with that. And I want you, if you haven't already, to open up that PDF that comes in the email with this link. And it'll have the lab manual. And go to page 1. Because page 1 is these 25 steps, these 25 observations that you're asked to do. And at the end of these 25, and so that's the part we will do together, we will do these 25. And then at the end, there is going to be some discussion questions. And that'll be true on all the labs. And that's the part that I won't do with you. That's the part that I'll stop and let you answer them. And you have a couple of ways. You could work with other students if you prefer to kind of go through those discussion questions. Or you can work on them on your own and just kind of answer them. But this, like I said, is the part that I will leave for you to kind of answer. And so we'll do what I like to call the raw data. We'll actually then, the stuff that we need the equipment for, the stuff that we need to be in the lab for, that's the part we will do together. The other parts like calculations and graphs and answering questions and drawing conclusions, whatever the lab is, that's the stuff I'll leave for you to do, where you can then hopefully answer those by seeing what I've done here with you. But if you can't, of course, that's your chance to ask some questions here. And so as I said in my email, I'm going to try to give you all the material for 1 week and let you kind of work through that during the week and shoot off questions as you have questions and I'll answer them. But that's why then I want to then kind of put a big block on Friday and just say, all right, now I'll turn on the Zoom meeting and say, all right, I'll be here for 5 hours and pop in so I can see your face if you want, or leave your camera off, doesn't really matter. I've got some learning how to do Zoom myself, so between now and Friday I got to figure out how I can do a couple things on Zoom. So hopefully the first session will go somewhat smoothly. But that's the design here, is that all this stuff you're learning here, which is really chapter 23 in the Survey book, or it's chapter 5 in the second volume of the OpenStax book, this is on the electric field. And just kind of that concept of what's going on. All right, well, maybe now is time to actually start the lab. Okay, I think you got this gist, and so that's what I'm getting at, is just always think of these online labs as me and you are partners. Okay, everybody has a partner, and I'm everybody's partner. Okay, and so you can just open it up. So hopefully by this time, you know, on your computer screen, or maybe you printed it out, you're looking here at page 1. And page 1 starts off by saying, you should know these 4 facts. Okay, and so these 4 facts come from the lecture. And so let me begin by just pointing out the obvious here. Fact number 1. It says here, all matter consists of electrically charged particles. Now let me take this opportunity to draw something here on the board. If you didn't quite get this out of the lecture, if you took any material, and I'll just pick one material that we're going to be working with here today. Here's a piece of vinyl. And so we're going to be working with this piece of vinyl. But it doesn't matter what the material is. A piece of aluminum, a piece of vinyl, a piece of lead. The idea here is that it would be made out of atoms. And every atom has a center part, a nucleus, and in that nucleus has these protons, and so they are positively charged. And that's going to be our focus. The charges. On the outside are the electrons, and so when this says all matter consists of electrically charged particles, this is what they're trying to say. They're trying to say everything's made out of atoms, and the atoms are made out of protons and electrons. And there's neutrons in there too, but as far as electricity is concerned, that's not a relevant discussion for us. We're only interested in the things that have charges, and so the protons and the electrons. Now, look at number 2. This is an important concept if you didn't get it out of the lecture. The negative charged units, that is the electrons, are the ones that are mobile. So if I were to maybe draw a second atom here in this picture, maybe even a third one, and I were to play with this material by maybe bringing another material to it, or maybe just in the material itself, the things that move around, the things that can break off from an atom and go to another atom are the electrons. And the electrons have this negative charge by our definition, thank you to Benjamin Franklin. And so the things that move are the negative. So keep that in mind. You're never going to hear me say, and hopefully you will never say it, that, oh, it's positive because the positives moved over blah, blah, blah. No. The positives do not move. At least in a solid. I should emphasize that. In a solid. Because in a solid, the positives are the atoms themselves. They're locked into place. And so keep that in mind as we move along. That the electrons are the stuff that are mobile. The stuff on the outside. Number 3. Equal numbers of positives and negatives make something neutral. Sometimes we like to say, when we hold up a piece of vinyl, we like to say, oh, this has no charge. That's misleading. We should really say this is neutral. And what we mean by that, it has no net charge. That is, there is an equal number of positives and negatives. Because hopefully what you learned in the lecture and what you'll see here in the lab is there is a lot of interaction going on between positives and negatives, or two positives or two negatives. And so it's important to realize that even though something has no net charge, that is, it's neutral, it still has a lot of charges. And you'll see that in these 25 steps we go through, that we will talk about that important distinction. When something is neutral, it's neutral. It's not that it doesn't have any charge, it's just neutral. All right. And the fourth and final thing is about conductors. And in particular, this says air is not a conductor. Now that word conductor, and hopefully this is what you got out of the lecture, but it's a good repeat here, means that the charges, and remember the ones that are mobile are the electrons, and so the electrons can move around. So maybe coming back here to my picture, if the electron can freely move from one atom to another, and so can move anywhere in that material, we call that a conductor. But if it can't move, that is this. If I were to take this one away, it would be missing a negative. And if it was what we call an insulator or a non-conductor, then that missing charge would actually stay in that same physical location. Whereas if it was a conductor, something like this might happen. Maybe the electron from the atom over here moves over. And so even though we took the electron away from this atom, it is now missing it right here. And one of the things that we will learn, and I don't think it was covered in the first lecture, so you may not have gotten this far quite yet, is that then the electrons, if you take them out of the middle of a conductor, things flow around, and the ones that are missing are at the surface of that conductor. In fact, I'm quite sure that that's chapter 25 or chapter 6 in the OpenStax book. So, no, well, it's Gauss's law. So I'm quite sure you haven't seen that. That's next week's material. So forgive me, I guess I'm getting ahead of myself here. But I am trying to point out that there is an important difference between a conductor and an insulator. And you're going to see that in the experiment today. You're going to then see the behavior. And so you will see as we go along for the rest of this semester that we will always ask ourselves, are we dealing with a conductor or are we dealing with an insulator? Because the behavior is very different. Can they move or can they not move? And that's crucial. So with that in mind, let's start these 25 steps. And here's what I want you to do. I want you to get out a piece of paper, or you can do it on a computer screen, whatever. And let's just run the 25 steps, the 25 experiments, make the observations, and just write down an answer. And that'll be half of the lab. And I said earlier, the other half of the lab then will be you then answering these 6 questions. All right, so I think finally we're ready to begin. I hope I didn't take too much time here at the beginning, but I did want to kind of set the stage for how we're going to do these labs in a remote setting. And I also, wanted to just take it extra slow to make sure you know those 4 facts. Those 4 facts are real important. You're going to see as we keep coming down to it. All right, so here we go. Step number 1, experiment number 1. And let's see what happens. It says here, suspend a pith ball or an aluminized plastic ball. Okay, so I'll stop right there. We already have that done for you right here. Here's a piece of wood. Here's this aluminum ball. The outside is painted with a small amount of aluminum paint. What I want to emphasize with this is, since you can't really touch it yourself, is that this outside coating is a conductor. It's made out of aluminum. And it's very, very light. And as you'll see, we want to see if it responds to any forces. That's why we want it to be light, but we also want it to be a conductor. And so note that we have a conductor, a very light conductor, hanging from a string. So that's what this first one. I'll read it again. Suspend a pith ball or an aluminized plastic ball by a thread and touch the ball with your fingers to quote unquote ground it. The ball will start off as neutral. Why is this? All right, so we don't really have an experiment to do other than to make sure this ball is neutral. And so as we begin our step 2, we need to know that that ball is neutral. But they're beginning to ask why. And so maybe that is best answered with a picture. Let me kind of get rid of this picture here. But if I were to take that aluminized ball right there, and so that'll be my ball there, And let's just say there were some extra electrons on it. So I'll put a little minus here, and a minus here, and a minus here, and a minus here, and a minus here. Now, remember, this is made out of aluminum. And aluminum has atomic number 13. So there are 13 protons in the nucleus. I won't bother to write out the 13. And then there are 13 electrons, and I won't bother to draw 13 electrons either. But if it's neutral, that would be an exact match, and you wouldn't have these extras on the outside. What they're trying to get at here is a property that hopefully you saw in the lecture, that we're also going to see here, that like charges repel each other. So if you had some extra electrons on here, and I probably could have drawn it a little better, they will push away from each other. And in this case, they repel one another, and so they'll spread out as far as they can get. So that's part of the reason they get on the surface, and they'll kind of evenly space themselves, at least if it's a sphere, so that they're the same distance apart. And of course, they can move around because it's a conductor. That's important here, okay? Now, watch what would happen if I came along with my finger. And so here is my finger. What does a finger look like? A little fingernail, a couple joints. All right, that's the best I can do. But here's my finger, and my finger comes along and touches that pith ball. You need to understand that the human body is a semi-good conductor itself. So, what would happen? Well, these negatives then have a chance to go somewhere further. And so what will happen is this one, because again, it's being repelled from that one and that one. Of course, it settled in the middle because they were kind of fighting each other, but now it goes, hey, I'm going to go over to here. And if my body's a conductor, it'll go not just on my finger, it'll go down my arm, and maybe it'll go all the way down to my toe. It's trying to get as far away, excuse me, it's trying to get as far away from these other ones as possible. Well, then of course, now the second one's going to go, well, wait a minute. I'm still being pushed by that one. Now, granted, that one's gone, but this one's still pushing me away. This one's way over on the toes somewhere over here. So then the second one goes. And then the third one goes. And here's the real key. If the object that is touching it, which is me, is much, much bigger than this little pit ball. So that was the key. I'm big, it's small. It can get, all these electrons can get far away from one another when they're on the big object compared to the small object. And so as a result, these guys push each other away, and they end up pushing them on the biggest object. And so this is why we want to touch it. We want to neutralize it. I know, because the like charges repel each other, that when I take a pit ball like this, a conductor like that, and it's small, and I touch it with something big, which is me, then they leave my small object and go on to the big object. Now, I suppose you may argue, maybe not the last electron. Okay. So these electrons, remember, are pretty small. And we're talking about billions and billions and billions. When you say you have some extra electron, it's not like I have an extra 5 like I drew on here, or 6 is what I drew on here. We're talking billions and billions. So if one stays on there, I'm going to call it neutral nonetheless. Okay? So maybe there's one electron still on it. But most of them went on to me. In fact, by extension of that, how would I get the electrons off of me? Yeah, and I hope you're guessing that, yeah, touch something bigger than me. Preferably a lot bigger than me. If it's only the same size as me, probably half of them go off and the other half remain on me. But what is the biggest object around? Yeah, the Earth, the ground. So when we like to neutralize our electronics, we call it grounding it, because the best way to make it neutral is to touch the biggest object, and the biggest object is the ground. For me, that's pretty easy. Watch, I'll just come over here, and I have a sink. And if I just grab this piece of metal, this pipe right here, this piece of pipe is a conductor. And it goes down and it's buried into the ground. And so now I am essentially touching Mother Earth. And these electrons have now left me. And so I'm neutral now. Of course, I don't think that was real relevant that I be neutral, but I wanted you to understand that word grounded. And of course, your author put it in quotes because you're not really touching the ground. You're touching it with a bigger object. And so that's what those third plugs are for. Maybe I'll grab a little device here. You know, this right here, this is what we call the grounding wire. Because when I plug in this apparatus, there's a little wire that runs through our walls. And literally that wire goes out the side of our building. And if you go over to the side of our building, that wire is then tied and clamped onto a copper rod. That copper rod is then pounded into the ground 20 feet. And so this right here is touching the ground, which is why it becomes a safety device. And so, you know, so no one hurts themselves. What we do is then we take this metal plate and we tie it to this wire, which is then connected to the ground. And so there is no way that this metal plate can ever develop a charge on it. Because if it started to, it would flow off and go to the biggest thing, which would be the ground. And so that way we will never electrocute ourselves. That's the idea there. Well, I digress, and I hopefully didn't use too much time there, but that first one is grounded. And so hopefully, and if you want to pause the video, this might be a good time, you can answer that question, why is this true? And you could keep it simple. You don't have to go into a long dialogue like I just did. Just say, you know, because like charges repel each other, they will push off to the biggest object, and therefore the small object will now be neutral. Maybe that's a good line. I'm not worried so much about your words. I'm just hopefully communicating with you that you're seeing this big picture. Why would touching it neutralize it? And I should emphasize, it's not just touching it, but it needs to be a conductor, and it also needs to be a small object. But if we meet all those conditions, which we do, then this is neutral. All right, so here's what I need to know here. So let me erase this picture here for just a second. And let me come back up here and draw then the pith ball and say, okay, now I'm ready for step 2, and I have a neutral pith ball. And I want to emphasize that. That was one of our 4 facts at the beginning. When I draw this pith ball, I won't put any pluses or minuses in here because my drawings, when I do pluses and minuses, those are the net charges. Those are the ones that are above or below I'll call it the par, if you will, when the two balance each other. And so right now I have 0 net charge. I've got a lot of positives and a lot of negatives, because here's what's kind of fun. So experiment number 2 says take a piece of acetate. So here's my acetate and a piece of wool. Bring the acetate near, rub them together and then bring it near. All right. So I'm going to start here by rubbing. Now let me just pause. Here I think is the advantage of the online labs, is I could say a little bit more than if you were just sitting there and rubbing it yourself. So if you didn't catch this out of the lecture, let me try to explain it now. But when you bring 2 materials together and you rub them like this, okay? And so maybe I'll take one material and another material, and I'll just make 2 rectangles here. But when you rub them, and so in this case wool and acetate, what touch each other are the stuff on the outside, which are the electrons. And so if you imagine an atom here and an atom here and an atom here, and on this material an atom, what's actually coming into contact are the electrons. And so when you rub them, you could actually end up scraping electrons, and you could scrape them off of both materials. It's kind of like, kind of in a weird imaginary way, if you think of King Kong, and King Kong picks up 2 cars, and he puts them together and rubs, it's the bumpers that touch. And it's the bumpers that rub off when he puts them together and rubs. And so these bumpers come flying off. And that's what's happening on a microscopic scale. Now they get attracted back. And if these are different materials, the way the positives are distributed in them are a little different in the acetate versus the wool. And without getting into the details of how they are distributed, which would be a fun topic in material science, and that's not exactly where we want to go here today, but they will attract the electrons back. And one will be stronger than the other. And so what will end up happening is the electrons will go more towards one than the other. Again, it's like King Kong and the cars and the bumpers. And you rub them. And if one car is, say, more magnetic than the other, and of course we're talking about electricity, not magnetism, so I hope I don't lose you in my analogy here. But if one car was magnetic and another one is not, when you knock off the two bumpers, those two bumpers will go to the car that has the magnet. And so that one will have extra electrons and the other one will be missing some electrons. And so what's going to end up happening is, let's just say the electrons go this way, then I'm going to say that this material becomes negative and this material lacking the negatives is now positives. So remember, it's the negatives that move. And so one of these materials becomes positive and one of them becomes negative. And so I am rubbing this. And at this point, they don't say which one it is, although I did say it in the lecture, so hopefully you know which one it is. But I'll leave that for step 7 as we try to discover which one it is. Or I think they tell us somewhere about step 7, or maybe it's a little later. 13. Well, it's coming up. I know that. All right. But anyways, here I am. I am rubbing it. And you know what? Maybe that's the advantage of the online lab. I'm going to tell you what it is, so there's no curiosity. I'm going to get a little bit ahead of the game, if you will. But I know, and you'll see this being proved later on, that when I rub this, the electrons are going to the wool. And so the acetate is now lacking electrons, which means it's positive. Okay, so here's my acetate. Okay, so what they want you to do in this one is really just an observation. Bring it near the pit ball and see if anything happens. Now remember, the pit ball is neutral. But they also say don't let it touch. So I'll do it again. And I hope you noticed that there is an attraction. It's not a very strong one, but there is a small amount of attraction. And that's what you should just write down. And so again, if you're in front of the computer screen here and you're answering your first online lab, question number 2, just say attraction. And maybe best if you put small attraction, because we're going to see a lot stronger attractions real soon. But they say don't let it touch. So I'm not going to, let it get too close there. Okay, so keep in mind, we'll talk about this later, that the pit ball was neutral and this was positive. All right, more on that to come. But let's go to step 3. Now, step 3 says try this a little different. It says charge the vinyl strip. All right, so I'm going to grab the other material. The other material is vinyl. I'm going to rub it. It says rub with the wool and bring the charged vinyl strip near the neutral pit ball. So it's, again, still should be neutral. I haven't, put any charges on it. There's no way any charges could get on it. Remember, the air, this was that point number 4 here. The air is a conductor. There's no way the electrons could come on and off after I touched it. When I touched it, I neutralized it. That was back in step 1. All right. Now, I'm going to just say the same thing happens here with the vinyl. That when I rub them, I'm going to free electrons. They're going to be attracted back to one material a little bit more than the other. We pick vinyl because vinyl really loves electrons. That's good and bad. You're going to see parts of these labs are going to be hard to show you things that happen because this thing sucks up electrons so well. But on the other things, this is nice because it sucks electrons so well. So with that in mind, as I do this, and I'm freeing up electrons when I rub it, and then they get attracted back, they mostly go to the vinyl. Okay? So vinyl now is negative. Keep that in mind. The pit ball is neutral. Keep that in mind. Bring it close, see what happens. Don't let it touch. Okay, maybe I'll do it a second time. But I'm hoping you see that it too attracted. There it is. Yep, definitely attracted. And we'll come back and talk about this a lot more. But remember, the acetate was positive and it attracted a neutral. That was step 2. But now the vinyl, that is now negative. It has more negatives than positives. We call it negative. It too attracted the neutral. And that's kind of interesting. But let's keep going here. All right. And so, by the way, I should say, so write down on step 3 that it attracted. And you could even say a small amount of attraction, because really that is kind of small. You'll see a lot more coming up here. All right, so let's go to step 4. Step 4 says now, charge the vinyl strip. Okay, here it is. By rubbing it with wool and touch, this time we're going to actually touch the vinyl strip to the pit ball. Okay, and then see what happens. All right, so I'm going to bring it close and touch it. Now, here's kind of the good and bad of our vinyl. So I'm going to touch it a couple of times. Finally, I'm getting to what you should be seeing. And I hope you see that when I let it touch this time, something different happens. It's repelling. And so at this point, why don't you just write down what you observe, because that's what step 4 is. They're not trying to get you to explain it quite yet, so I'll hold off on explaining it, but that's coming up here. So what happens? It repels. Now, step 5 says bring the acetate, all right? So now just to remember, when I rub the acetate's positive. Let me bring it near the pit ball. And you will see that there's attraction. And I'm hoping you see there's a little more attraction than there was before when we did this back in step 2. And we'll talk about the physics of it coming up here. But the